Okay, go ahead.
Hi, good morning, everyone. My topic today is about Boost Compute Library. In our group, almost everyone needs to write projects about image processing, which containing a lot of large and complex metric calculating. So basically, you need to do a lot of metric computing. So in this case, the Boost Compute Library is a very helpful and powerful tool that in large metric calculation, which can save you a lot of time. The Boost Compute is a C++ library for multi-core CPU and GPU computing based on OpenCL. It can also be comprehended as STL for parallel devices. The parallel devices are in widely range of GPUs like NVIDIA, AMD, and Intel, and multi-core CPUs like what we have in our computer these days, AMD and Intel most. It also includes some accelerators and FPGAs. So basically, the basic design for Boost Compute Library looks like this. At the bottom, these are some hardware parallel devices like GPU or multi-core CPU or FPGA. On top of that, the Boost Compute uses OpenCL to talk to the hardware devices so that we can choose whatever the devices we want to use. Normally, when we do some programming computing, the system automatically chooses CPU device for calculation. But by using Boost Compute Library, we can choose a GPU or a multi-core CPU instead of CPU when we want to calculate the complex or large metrics. So it can save you a lot of time and it's more efficient to using GPU, something like that. And on top of that, the Boost Compute Library provides the low-level API and STL-like API, which means that we can use C++ language to implement our calculation. Like you can use the containers, the iterators, and most of the algorithms in the STL library. So how to use the Boost Compute Library? The first, you need to install the Boost. I think every one of our group has already installed the Boost in our computer. So then the Boost Compute is very easy to use. Because it's just a header-only compute library. So no linking is required. Like the command here, you can just use the code here to compile by replace the paste to compute by the repository of your compute file in your computer, and then compile it. It should be work. And all the header files are included in boostcompute.hpp file, and all the functions and classes can be brought into a global scape by using a namespace. So what's the low-level API? Low-level API provides C++ API over a C API provided by the OpenCL library. it includes many classes that you can use to computing the OpenCL, like OpenCL project objects, like the buffers and contexts and the command queue. These are the basic lines of low-level APIs. The first line of code here is to get the default device. This command line. It uses boost compute default device function to basically looks up the default device we want to choose on system. The OpenCL library provides enumerate OpenCL implementations on system, and each implementation has one or more devices which you can choose from. And by using this code, you can it just looks up the list of the devices and choose the one we think should be the best. Normally, the devices we choose is GPU or multi-core CPU. And the next line of code here is to create OpenCL context for the device. OpenCL context is a kind of a state. It provides a places where you can allocate your memory buffers. And the next line of code here create command queue for the device. The command queue are OpenCL ways of initiating the work to be done on compute boost. So you can initiate the buffers, the memory buffers between the host and the device you choose. The last line is just print out the device's name. So those lines of command are the pretty commonly used command lines, which exist in any application that if you want to use GPU or multi-core CPU to calculate the code. Here is a simple example of how to use boost compute. The first line of the code, the first 3 lines of the code is what I just introduced to get default device and setup context. And then it can generate random data on the host by using the vector container and generate and run algorithms. And then it can create the vector on the device, which provides the context that you can allocate your memories. And then it transfers data from the host to the device by using copy function. And then it calculates the square root of each element in place by using transform function. At the last sentence, it copies the values back to the host by using copy function again. So it finished the process by choosing the default device and set up the context and calculating our data in the default device we choose, and then send the data back to the host. Based on the low-level APIs, there are some advanced topics like vector data type, custom functions, custom types, and so on. I mainly choose some topics that I think will be useful for us to introduce. The first is the vector data type. In addition to built-in types like int and float, the OpenCL also provides vector data types for in the format shows here. The scalar means the scalar data type like int, float, and char, and the n here is the size of the vector. So as you can see in the points, each row has 4 elements in float type, and as the code below, we can use float 4 underline to express the data elements here. And the next is custom functions. In Boost Compute function, macro creates function objects in C++, which can be executed on the GPU by OpenCL with the Boost Compute algorithms in the form like below. You can see in the example, the Boost Compute function is the macro command, and the bool here is the return type, and the compare lines is the function name. The float A and float B is the argument list. And here is the source code. So this function is to return the true if the length of the first is less than the second. And in the second example, the int is the return type, add4 is the function name, int is the argument type, and the source code is x plus 4. Next is Lambda Expressions. Lambda Expressions uses underline plus number to indicate the arguments, like the format here. The following examples shows how to use Lambda Expressions along the Boost Compute calculation. The first is to count the odd number in the vector. And the second example is to multiply each element in the vector by 3 and subtract 4. The last example shows how Lambda expressions can be used in build functions. And the last one is asynchronous operations. According to the author says, there is a big bottleneck of the Boost Compute library, which is the memory transfers. So we can use the function copy asynchronous to alleviate the bottleneck. It allows us to perform other work on the host or device when data transferring. So it basically to overlap the memory when transferring the memory buffers. And that's all. Thank you.
What's OpenCL library? Let's clear about that. I know OpenCL, but I'm not quite sure about OpenCL.
OpenCL is kind of a commonly used language API library.
Yeah, it's like a industry standard API, but for what?
For all the libraries that in different right manner.
It's for parallel computing.
Yeah, I mean, like you have OpenCL and OpenGL, like both of them are often associated with GPUs because you can use OpenCL to do, it's like a programming, it's basically an API for doing, like you said, basically doing parallel processing with GPUs, for example, or other devices. So you may actually be using a GPU, for example, using OpenCL, but the interface is not for graphics. Like it's just for general purpose computation, whereas OpenGL, it's specifically like the whole interface is for doing graphic stuff, and pretty much the only thing you can do is graphic stuff. So OpenCL is a more general computation interface where it's not intended for graphics. But it's an industry standard. I don't know if it's from maybe you might know, Stephen. I'm not sure if it's from the same group as OpenGL, but it's basically a de facto industry standard. Like a lot of people use it. It's not an ISO standard though. Hopefully that made some sense. And I guess the reason they chose to use OpenCL is that many platforms have support for OpenCL, so by using it in Boost, then it will mean that they can support more different types of devices. Okay, because if you're a GPU manufacturer, you will provide OpenGL implementation for your hardware. Otherwise, people won't be able to use it efficiently. Probably also you provide OpenCL support as well. It's kind of the two popular standards.
Let's go back to the slides where you do something like compare the lens. I'm wondering what's the difference between the size of in the standard library and this example?
Here it has the vector data type we built in ourselves, and here maybe the difference between the size algorithm, between the size function in standard library, but that's what I guess. But I think it also could be just a simple examples that to show you how to build functions by build custom functions. So if the standard library could allow the vector data type, then it has no difference with the size function in standard library.
Just one thing to clarify. It's the length, like the length of the vector. It's not like the number of elements in the vector, right? So like because otherwise it would seem kind of useless if it returned the size of the vector, because I assume that float 4 is like length 4 always. So I guess the length is the length of the vector. Is that what it is? Like I don't know the details of Boost Compute. I've never actually used it, but I'm just kind of generally familiar with what it does. So this is actually a very interesting presentation for me because I don't know the details. But maybe one other question is the float 4 underscore. Is that like a type that's defined in the Boost Compute library, or is this something in your example, maybe somewhere on some other slide you created yourself?
Yeah, it's a vector data type here.
Okay, so it's like built into the library. So if you want to like 4 float array, the 4 float vector, you use this built-in type to the library. Okay. Maybe one other question: is there like other? Well, I guess maybe you said on the other slide, there other values of n. Like, is there a float 3? Because I could imagine a lot of applications might use like a 3-dimensional, like you're doing 3-dimensional stuff. So maybe having 3 coordinates would be useful. When you say scalar n, does it allow pretty much any n that you want to use, or is it just maybe like 3, 4, and 2 or something?
Any size of the vector you want to use.
Okay.
No matter it's beautiful.
Okay, that's good.
So it could be 1 million or even larger.
Yeah, I think so. But the examples just show us at almost I just see the number 4 in the examples. I didn't see like 100 or million something.
I would guess probably in practice 2, 3, and 4 would be the most common. Like 2 if you're doing 2-dimensional graphics, 3 if you're maybe like doing 3-dimensional stuff, and then 4 if you're using homogeneous coordinates for 3-dimensional stuff. That would be what I would guess would be most common. But certainly you could have other dimensions too. That was what I was asking. Any other questions? Or suggestions in terms of presentations?
Add the slides.
What was that?
Add the slides.
Oh yeah, I was going to say that too. Please always include slide numbers on your slides, because actually, if people want to ask questions at the end, the natural way to say what the question is about is say, could you please go to slide 13? If you don't put slides on it, it makes it really hard for people to ask meaningful questions, because you spend a lot of time flipping through the slides. Is this the one you mean? Is this the one you mean? And so on.
Thanks for the suggestion.
I generally would make that suggestion to anyone. Like, if you're giving a presentation, always put numbers on the slides, because it's inconvenient to people if they can't refer to the slide number.
Sure. And I try to implement the Compute Boost library in my laptop, but I don't know the reason why. When I use G++ to compile the command, the Boost Compute library can't link with the OpenCL library, can't link with the system OpenCL library in my laptop, so I didn't compare successfully. But as the instruction, it should be very easy to implement.
Yeah, without seeing the exact errors and things you're getting, it would be difficult to say, because there's lots of things that potentially could go wrong. I guess if anyone really want to try this, also there's the SDE environment on the lab machines that I install. It has the most recent version of Boost, like the 1.67 point something, which definitely will have this, because you said it's from 1.61 onwards, so it's definitely included in that. I don't know if it's on the default installed system version of Boost, because the lab machines also have Boost installed that came with the operating system, but the C++ compiler on those machines I think is 3 years old. Boost maybe 3 or 4 years old, and it might not have 1.61, it might be 1.5 something, so I'm not sure if it's on the lab machines. I don't know, did you try? Maybe you were just trying on your notebook. If things don't work on your notebook, you're trying to get it working, you can always try on the lab machines. You might have more luck with the SDE environment, though, rather than just the default installed ones. But I haven't actually tried Boost Compute at all, on any machine, so I can't really comment on that. But it might work.
Search some videos